Good evening, everyone. I feel I ought to start with an apology for inflicting myself upon you 2 months in a row, because it so happens that I gave a talk here last month. But as Mike said, it was necessary to step in for this one, and I had agreed to give a talk to the retired engineers in Worthing, actually in September. And so I thought, oh, I can quickly put some slides together and try it out on my IET colleagues. So that's what I'm going to try and do tonight. If any of you of a certain age are interested in afternoon talks and the occasional visit and so on, then just search for Retired Engineers Worthing and you'll get to their website. Another thing just to mention, you'll notice there's a camera here. So if you've missed any of our past talks, most of them are videoed and up on our YouTube channel. Again, you can get to that from our homepage, or just, again, search on YouTube for IET Sussex. Right, yes, Mike said I would introduce myself, and really it's about my connection with small modular reactors. Well, basically there isn't any, except that. As a physicist, I started my career working on the design of nuclear reactors for submarines and then for commercial power plants. More precisely, I worked on the tools that were being used for the design, but I have a bit of a background. Unfortunately, they kept cancelling the contracts and they never built anything I ever worked on, so that's when I switched to industrial process control. But I've always kept an interest in reactor design and what's been going on. And so tonight I thought I would try and lead you through a little bit of the history. I thought I might start with just updating people or making sure everyone's just on the same page as far as the physics is concerned for nuclear fission. I'll have a quick look at reactor types. See, not all the varieties of reactors, because there's a lot of them, but just the basic two concepts. And I thought it would be useful to have a quick look at the history of UK nuclear power within the UK. You'll notice on the first slide I'd actually put UK in brackets after small modular reactors, because I'm really just going to concentrate on the UK and not the rest of the world. Then we'll get down to why we're here, small modular reactors, and if we have time, then it might be informative just to look at where people think things might go beyond the realm of the small modular reactor. Okay, some basics. I'll talk really about nuclear fission, a little bit about fuel cycles, and again those reactor types. So you're all aware that if a uranium-235 nucleus captures a neutron, then it creates another isotope, uranium-236, which doesn't last very long, and it splits up into fission products. They're just examples. There's a whole range of different products that are produced. And it emits some neutrons, usually 2 or 3. And it's those neutrons then that are captured by additional uranium atoms that cause the chain reaction to go on. Just as an aside, the energy released from a U-235 fission is about 50 million times more than burning an atom of carbon. So you can see that there's quite an incentive to try and use nuclear power compared to things like coal-fired power stations. Those neutrons that come out of there are traveling pretty fast. In fact, around about 20,000 kilometers per second. I don't know who measured it, but anyway, that's what it's thought. But there is, as we'll see in a moment, some benefit to slowing them down to what's generally referred to as thermal neutron speeds. In other words, they're in thermal equilibrium with the matter that's around them. And that's a mere 2 kilometers per second. Now, that's important because if you look at what's called the neutron cross-section for these nuclei, that's, if you like, the probability that they will capture a neutron. And you'll see that for the fast sorry, wrong button. For the fast neutrons up in this region, this is the neutrons with energies that, that are produced on fission. The probability of them being captured is fairly low. But if you slow them down, and bearing in mind this is a logarithmic scale, as is this one, then there's much greater chance of them being captured and producing a fission. It's interesting that the scale here is in a unit called barns. Now, as I understand it, when they first measured this, someone said, crikey, it's as big as a barn door. And thus the unit barn. And it's interesting to note that for uranium-235, and that its probability of capturing a fast neutron is about 1 barn. You'll notice, just for reference in a moment, that uranium-238 is way up here. In other words, it only captures very fast neutrons. So if we look now at the fuel cycles, there's a couple of them, uranium fuel cycle and thorium fuel cycle, which we'll come on to in a moment. So natural uranium is mainly uranium-238, but with just a very small amount of uranium-235, and it's 235 that is fissionable. 238 is not. However, if a uranium-238 isotope captures a neutron, then it becomes uranium-239, and that quickly decays to become neptunium, which in turn quickly decays to become plutonium. A beta particle, by the way, if that's not familiar, it's really just an electron. So what you have when a beta particle is emitted, you're left, essentially a neutron is converted into a proton and an electron that's being spit out. So that means that it is possible for uranium-238 to turn into something that is fissionable and can produce power, and we'll mention that a little bit later. The thorium fuel cycle, again, thorium is not fissionable, but it's what they call fertile. And in a way, uranium-238 is fertile, basically in that it can be converted into something that will fission. So here, a neutron into thorium creates the next isotope of thorium, beta decay, palladium, another beta decay, and we have the isotope U-233, which isn't a naturally occurring isotope of uranium, but it is fissionable. And so there's some benefit to using this. In fact, thorium is more abundant than uranium, so I'm told. I'm not quite sure what the physical and nuclear properties are that are superior to uranium, but I'm again told there are some. It really, I guess these two are related in that if you use the thorium cycle, then you don't produce plutonium. You don't produce ingredients that can be used within weapons. Of course, both the US and the UK wanted to produce plutonium. And so all the research and all the energy went into the uranium fuel cycle. There has been some research on the thorium fuel cycle, but very minor amount of work compared to using uranium. Okay, we've talked about fast neutrons and thermal neutrons, and they're basically the different types of reactor. There's lots of variations within those, but there are those two types. I'm told, I think it was on Wikipedia, that there are about 20 fast reactors in operation around the world. So you can probably guess that most of them are thermal reactors. And in a thermal reactor, you have to slow down those neutrons. They call them, moderate them. And the likes of water and graphite are good at moderating, at allowing neutrons to bounce around between them and absorb some of the energy. There are other things that can be used for moderation. And you've probably heard the term heavy water. Now that's water with the hydrogen atoms replaced with deuterium, the next isotope of hydrogen. And I think there's something like 5% of seawater is deuterium. So there is a source for that. And heavy water moderated reactors have been produced around the world. Also, you have to cool them. And so water and gas cooled reactors are common, but there are some others, and we'll come on to mention two of those a bit later on. Of course, any reactor, you need some fuel. If it's a thermal reactor, you need a moderator. There's going to be the need to have control rods, devices that will mop up neutrons and therefore stop or control the chain reaction. You're going to need some form of coolant. It's likely you're going to have to put it in some sort of vessel that will withstand the pressures of the coolant. And at the end of the day, you're going to produce heat, so you need some means of generating steam and converting it into electricity. And usually there's, always, there's some form of containment around the whole thing, so as to try and keep anything nasty in the area. Okay, that's as much as I was going to say about some of the basics. Let's look at some of the history of the nuclear reactors in the UK, just very briefly. I mean, it started, wrong button again, started in the mid-1950s with what was known as the Magnox reactors. I'll say a little bit more about each of these in a moment, so don't worry about the name Magnox. But then we had the advanced gas-cooled reactors, and currently it's pressurized water reactors that are being built in the UK. Of course, many of these, all the Magnox reactors have been shut down and decommissioned. Some of the AGRs have been shut down also. I think there's only 4 left that are actually producing power. So, Magnox reactors. Magnox is magnesium non-oxidizing. It's used to contain the fuel elements. So the fuel is put into Magnox enclosures and pressurized with helium. So here you have a reactor core made up of these Magnox tubes filled with natural uranium. So that's uranium, mainly uranium-238, but with a small amount of uranium-235. These are the control rods that are coming down to try and help control the chain reaction. There is, in this case, carbon dioxide being pumped around to cool it, and that carbon dioxide then going out of the pressure vessel into a heat exchanger. The control rods, by the way, as it says here, are boron steel. Boron has a very high capture cross-section for neutrons, thermal neutrons in particular, and so it's a good way of mopping up unwanted neutrons. One of the big advantages of this type of reactor is that it can be refueled online. You've probably seen photographs of big refueling machines sat on top of a deck of a nuclear reactor. They move it around, open up, pull out a fuel rod, push a new one in, seal it up, and move on. All really very clever, but quite an advantage to keep things running all the time. The Magnox reactors were generally in the range 300 to 490 megawatts. Okay, and so they're within a pressure vessel, and then a containment building of some sort. So that was Magnox, as I say there. Oh, yes, I should mention that Calder Hall was the first in 1956. When it comes to AGRs, then it basically has the same components, except that the fuel now is enriched uranium. So 2.5 to 3.5% of U-235. Again, it's graphite moderated. Again, carbon dioxide cooled. So we have the reactor core. This time, though, the heat exchangers are within the pressure vessel. This is a concrete pressure vessel. Interestingly, the outlet temperature from these reactors, it was designed so that they would match what was coming out of coal-fired power stations, which meant that they could just use the existing turbines and the electricity generation equipment that had been used for many years. Also, again, online refueling. So the reactor just could be continually refueled over its life cycle. And there was a range of power outputs from 880 to 1220. 7 twin reactor stations were built, and as I said, I think there's only 4 left that are still producing electricity. Dungeness B actually was the first to produce electricity in 1983, but note that it was 13 years late in its delivery. So late nuclear projects are not a new phenomenon at all. Okay, but now we're building pressurized water reactors. And to be honest, pressurized water reactors have been the main type of reactor that have been produced around the world. There must be more of them than any of the other types. So we still have here a pressure vessel, steel pressure vessel, with the reactor core within it. Because there's a pressure of something of the order of 2000 psi, it needs a separate pressurizer to keep the pressure up. And then this is a 4-loop system. So we have 4 heat exchangers with pumps pumping the coolant around. Remember, the coolant is water, and so it's both a moderator and a coolant. This is a typical arrangement. The reactor core down here, control rods above with mechanisms to move the rods in and out, and then inlet and outlet pipes going to each of the heat exchangers and pumps. At the moment, Hinkley Point C is under construction. Well, and a sizable C in Suffolk is also under construction, but only for about a year, so I'm not sure quite how far they've got on with that. Construction of Hinkley Point started in 2017, and Unit 1, there's 2 reactors to be built. Unit 1 is going to be operational, some people say between 2029 and 2031, and I think that's probably EDF who are building it, but some people feel that it may be as late as 2036. The fuel in these is uranium enriched uranium dioxide, and it's a 4-loop system as in the diagram we saw before. And it costs a staggering amount. I think I read somewhere that it's currently estimated to be 50% higher than the original cost. By the way, Hinkley Point C was originally due to be operational in 2 years' time. So it's going to be another late nuclear project. Right, that's all I was going to say about the history. Now we're getting down to why we're here. So sorry it's taken a while, but we're finally on to small modular reactors. I'll try and answer the question, what is a small modular reactor? And then I'll talk a bit about the UK competition, which you may or may not know about. Then we'll look at the technologies that the current contenders for building them are proposing to use, and then a brief look at the timescale. So what is an SMR? Well, As I said at the beginning, I got involved in the military use of reactors. And typically the small reactors have been used in various types of marine craft. They're generally fairly low powered. They're normally trying to turn a propeller shaft, although of course they do produce electricity. There's still a generator there because the vessel needs electricity. But their main purpose is to turn that propeller shaft, one or more of them. And I don't know if you're planning to ever go on one of these, but there are fewer safety systems on them, mainly because of lack of space and perhaps because they're military. They're not subject to the regulations that you find in all of the countries where they're going to be placed. Okay. Again, according to Wikipedia, there's 80 different designs of small modular reactor around the world. So we're only going to look at 4 of them, the ones that are going to be built in the UK or are in the process of it. As far as I'm aware, there's only 2 actually working at the moment, reactors that can be called small modular reactors, although another 6 are under construction. And I say what they can be called because answering that question, what is an SMR, really it's all in the name. You know, they are small, up to 300 megawatts per unit. So you can build as many as you need for the location in which you're wanting to produce the power. And they're modular. Whoops, wrong one. They're modular. They're like an IKEA wardrobe. You know, their bits are made in a factory and it's assembled on site. Yes, there's still a lot of building work to be done. There's all the infrastructure and buildings and whatever, but the power plant itself, built in a factory, hopefully under controlled conditions, repeatable, and it's hopefully cheaper, and then shipped to site and assembled. And so that's basically it for a small modular reactor. You know, it is small in terms of its power output, and it can be built more or less on a production line basis. Now, in 2023, the government said it was intent on placing orders. Final investment decision means actually giving an order to a company to produce something. That there would be orders for 2 of them placed within the next Parliament. I don't know, there was an election in between, so perhaps that, I'm not sure quite how that fits in. But again in 2023, the Energy Secretary launched an international competition to select 4 different SMR technologies to go through that detailed design phase. And it's not just the design, but it's going through all the regulatory approvals and possibly also placing orders for long lead time items. So Great British Nuclear, I think it's sort of comes under the umbrella of British Nuclear Fuels these days. Not quite sure of the contractual arrangements there, but it was set up to deal with all of our nuclear futures. And they, at the same time, invited interested parties. And in October, they selected 6 technologies. So here they're not looking at the economics of it or the costs of it, they're just looking at the technologies to see which ones they think might be most appropriate. In 2024, they invited 6 parties to bid in the next phase, but only 5 were received by the deadline. I think it was probably EDF who pulled out, if my memory serves me correctly. So they selected 4 companies. The 4 companies are Rolls-Royce SMR, Holtec Britain, GE Hitachi, and Westinghouse. And I'll go through the technologies that each of these are proposing in a moment. And they issued this invitation to negotiate. In February of this year, they invited invited them to give their submit their final tenders for this next part of the process. Now we'll talk about where things go from here in a little while, but first we'll just go through each of these and look at the technologies that they provide. Surprisingly, it's very difficult to find out details of these. They've all submitted lots of documents to Great British Nuclear. One of them, I think it was Westinghouse, has published those, but all the diagrams are missing. There's lots of bits removed from the documents. So, I guess there's commercial reasons why they're not making much information available. They're very good at the marketing diagrams and pretty pictures, and I'm afraid you'll see some of those in just a moment. So, okay, let's go through. Rolls-Royce SMR, they call it the UK SMR. That's their sort of tag name for this design. And it's a close-coupled 3-loop system. Wrong one again, never mind. So although this diagram just shows the 1 loop, there are actually 3 of them. Now, interestingly, the power output is 470 megawatts. Now that's bigger than what is generally considered as a small reactor. And as you can see here, most of the Magnox reactors were actually less powerful than that. So small-ish, perhaps. Just to provide context, of course, Hinkley Point, each of the reactors is 1,600 megawatts. So they're certainly much smaller than what is currently being built. So they're proposing to use enriched uranium dioxide. They say that the build time is 4 years. 2 years for that site preparation, because there's quite a lot there. And during that period, of course, they're manufacturing the components that are then going to be assembled and commissioned over the next 2 years. I don't know if you're aware, but Rolls-Royce SMR is actually 20% owned by a Czech consortium of companies. And they've already decided that they're going to build a number of these reactors in Czechoslovakia. That's their plan. We'll see whether it happens. This is one of the glosses from Rolls-Royce. The interesting point is that they intend to build this site canopy. So having built all the foundations and the raft on which this whole thing is going to sit, they're going to build a canopy over the whole lot and then build what's underneath it. So there won't be problems with weather or temperature or access. They can build it all within this canopy. As I said, it's a 3-loop system, so you have a pressure vessel here, your pressurizer, and 3 heat exchangers, along with pumps to pump the coolant round. And this was the only image I could find of the actual internals of the reactor. So the core will be in this area. There's various guides to bring fuel rods down into the reactor, and the coolant comes up from the bottom and out through the ports to the steam generators. Okay, so that's an overview of what Rolls-Royce are proposing. Holtec Britain is proposing what they call SMR 300, which has an output of 300 megawatts. So same arrangement, reactor core, steam generator, and then a conventional plant to generate electricity. All sat within a pressure vessel and then containment around it. So nothing unusual. Uranium dioxide fuel, but they do say that the core is located deep underground, protected by steel and concrete containment enclosure. And that it's always deeply submerged. And if you notice here, there's this annular reservoir. So there is a blanket of water around, which I'm assuming is both as additional radiation protection as well as a means of cooling if something goes wrong. They do say, however, that the safety systems are all passive, what they call walk-away safe. So if the reactor's shut down or the rods drop in, the nuclear reaction is shut down, it doesn't then require any power to dispose of the decay heat that's left in the system. Oh yes, Holtec Britain is actually a US-based company with a joint memorandum of understanding with Balfour Beatty and Hyundai Engineering. Interestingly, they were very keen to point out that they were offering quite a lot of money to the UK to build a factory in South Yorkshire. I guess that's the sort of thing that can influence politicians. They have this schematic of what their plant might look like. There's obviously here 2 reactor systems with a turbine hall and all the other paraphernalia that you might need. The only diagram of what the system might look like that I could find is actually of a slightly different reactor. They have this SMR 160, which I assume is a 160 megawatt system, is a land-based version of the reactors that are in aircraft carriers. So here you can see the reactor core, in a pressure vessel. This only has a single loop, but one can imagine that the SMR 300 is slightly larger and has the 2 loops. Hitachi now is something slightly different. It's a boiling water reactor. And so you'll notice there's still a pressure vessel, and there's a reactor core down here. But the water that's used to cool it, and as a moderator, of course, is allowed to boil. And it's the steam from that that is brought out of the containment area and passed through turbines. To me, I'm not so sure about that sort of concept, but boiling water reactors have been used successfully around the world. And the advantage that they have, of course, is they don't need those heat exchangers, separate heat exchangers to use the heat to generate steam. The steam is produced as part of the system. They claim it's natural circulation, but I guess they mean that that's the case if the system's shut down, there'll be natural circulation. Again, enriched fuel. They mention that this refueling is required for 12 to 24 months. Now, actually, I should have mentioned earlier, let's see if I can go back to just this as an example. To refuel a PWR, you have to unbolt the top of the pressure vessel, take out all the gubbins that's above the core, and then, well, either lift out the entire pressure vessel intact and replace it with another one, or if you're keeping the pressure vessel, put a new core in and put all the other gubbins back. So it's quite an event to refuel a PWR. And I guess that's why generally people want 2 reactors on the site, so that when it comes time of refueling, one of them can be shut down to refuel. And it's the same, therefore, with the boiling water reactor. Again, you need to either remove the whole pressure vessel or take the top off and then take out the core. Just as an aside, and I don't think it's classified in any way, but on submarines, they cut a hole in the top of the submarine and yank out the whole pressure vessel and replace it with another one. So where did we get with this? Yes, recycling, and then a fully passive safety system. Notice a big tank of water up here. I'm sure that has something to do with their safety system. They weren't very forthcoming. This GNF2 fuel, apparently it is a standard existing fuel assembly that is used in other reactors. So they can use something that already exists and create bundles. And the reactor is 4 meters in diameter, internal diameter. Hinkley Point is about 4 or 5 times bigger than that. And they say it has a design life of 60 years. And here we can see how it's the reactor, which is, there's the pressure vessel, the reactor's down in the bottom of it. This is clearly underground. There's water all around it, as well as a tank of water at the top. And if you look at the cutaway of the pressure vessel, then here's the reactor core, here's the separator to separate out the steam and then to dry the steam before pushing it out. But because you have all this gubbins up at the top, it means that your control rods have to come in from the bottom. Again, normal practice is to let gravity or assisted gravity push them down rather than have something that's got to push them up. But if you've got all that stuff at the top, you can't do that. So here, normal reactor system with turbines nearby to produce electricity. Now they are actually building 2 of these reactors at the moment, one in Canada and one in Poland. I haven't been able to find out when they're due to be finished, but at least they're in the process of being built. And the final one of our set of 4 is from Westinghouse, the AP300, and so it's based on the AP1000, which is an existing system. So they're already built and operating. And so they've scaled it down to make a single loop PWR, again with that 300 megawatt output. Again, because they have, I guess, on this system, this technology for their fuel, they're adopting that for this system. And in fact, I think we can say it's described as pellets of chromia and alumina doped uranium oxide pellets. So, but I think the main point is that it's something that's already in use and so should be lower risk. It says that it requires a lot of these assemblies and there's a 4-year recycling system. But otherwise it's the same sort of thing, reactor, reactor system, pressurizer, steam generator, but just a 1-loop system. And again, they like the nice diagrams. So here is the pressure vessel with water all around it and the tank of water above. It's a single loop system, so pressure vessel with a reactor, steam generator, and a pressurizer. And this is just a diagram of that array of fuel, which is in current use in other reactors. Similarly with the control rods, they've got an existing design that they can use and transfer across. Okay. Timescale. Now, we're all aware that the amount of power that the UK can generate has been falling. Well, I guess the demand has been falling, and so what we're producing is falling. Obviously, coal has dropped off completely. Gas has stayed roughly the same with a little bit of ups and downs. A lot more renewable energy, but less nuclear than we've had in the past. And I think, as I said before, there are only 4 existing AGRs operating, but with proposals to build others at Hinkley Point, at other places within the UK. I think a little while ago the one at Wilfer was abandoned, or the people who were going to build it pulled out. So we started, or we left the timeline a little while ago with this invitation in April 2023. And it's this summer where they're going to select, and it says here 2 vendors, but the chief executive of Great British Nuclear gave an interview where he said they would be selecting 1, 2 or 3 suppliers. So I don't know. I had always believed that it was going to be 2 vendors and they'd place an order on each of them so as to have some alternative choices. But that final investment decision is not until the end of 2029. And Rolls-Royce say it's going to take 4 years to build one, so it's going to be well into the 2030s before the first SMR is operational. Looking right back, the original intent was to have the first operational in 2030. So things have moved a bit. And however, it was reported just a week ago that in this spring statement that's coming up, the Chancellor is expected to halve the number of SMRs. So it looks as though it may be a means of saving money in the short term at the expense of our sort of long-term energy security.
Expensive power cuts.
Yeah. So we will see. Now, if you're still awake, what we could do is just have a look at some ideas. I'll just flash through these so that you get a flavour of what people are thinking of. Beyond the SMR, the SMRs are built with what is essentially the current technology, generally known as Generation 3 of nuclear power plants. But Generation 4 is going to be a different type of technology. In fact, there was an energy white paper, Powering Our Net Zero Future, released in 2020, and a 10-point plan for green industrial revolution, again in 2020, that caused the Nuclear Innovation and Research Office to produce an Advanced Modular Reactors technical assessment. So that was given to the government in 2021. They came up with 6 types of technology that they thought would be worthwhile looking at in the future. And I'll just run through them very briefly. Don't worry about the list for the moment. This one is a very high temperature gas reactor. So it's interesting that it's graphite moderated, this time cooled by helium, not by carbon dioxide. But it's rather like the advanced gas-cooled reactor. You can read that if you want, but these particles, the fuel is made up of small particles of uranium that are coated in carbon and silicon carbide. But otherwise, it's sort of conventional in that you have within this black blob some sort of reactor core, control rods coming from the front or in a pressure vessel, and helium pumped through and out into a heat exchanger. And it's very high temperature. So we're talking of an outlet temperature in those ranges, which makes it quite versatile. A sodium-cooled fast reactor is one of these variants of a number of things. Firstly, it's a fast reactor, so there's no moderation. They're not reducing the speed of the neutrons. And it's sodium that's being passed around the system and through an external heat exchanger. It's a higher power density, which means it can be quite compact, low pressure, a slightly lower outlet temperature, and they're using a mixture of uranium and plutonium. So it's an opportunity to dispose of a lot of the plutonium that might be lying around. It's claimed that it can use natural circulation to remove the decay heat, and then there's no oxygen there, so corrosion should be better. Now we've had sodium cooled, and this is lead cooled. So molten lead being pumped around through the reactor core to take away the heat. Again, mixed oxide fuel. Again, a closed fuel cycle. I didn't mention it. By closed fuel cycle, they mean that once you take the fuel out, you can process it and reclaim whatever's left in it to reuse again. That high temperature gas reactor actually was an open system. The spent fuel that comes out is just going to waste. And they claim that this is a very efficient secondary cycle. I think they're normally around 35%-ish as a sort of efficiency of taking the heat from the reactor and converting it into electricity. And interestingly, that runs at atmospheric pressure. So the whole pressure business really becomes a container and containment. A molten salt reactor. This is interesting in the sense that the molten salt contains both the fuel, it acts as a coolant, and if it's a thermal design, it can act as the moderator as well. So you're bringing this molten salt into an area where the conditions are right for fission to occur, but then taking it out and putting it through heat exchangers. There are quite a few designs. Some of them are for thermal reactors and some of them from fast reactors. A supercritical water-cooled reactor, very high pressure. So whereas we're talking of about 2,000 psi for a pressurized water reactor, this is half as much again. And again, there's designs for both thermal and fast types of reactors. And again, they claim a very high efficiency and a very simple design. The final one, you'll be pleased to hear, is the gas-cooled fast reactor. So again, that's sort of a combination of the things we've been talking about. Helium-cooled, but a fast reactor, so no moderation required, pretty high temperatures, and again, a closed fuel cycle. So again, we have the reactor. For some reason that I don't understand, they've got control rods coming in from the bottom, but going through a heat exchanger and then through the standard thing. So that's just a flavour of the sort of technologies that are being looked at for the stage beyond the SMR. And they assessed these technologies against a whole range of criteria and came to the conclusion that the high temperature gas reactor was the most promising for future development. One point that came out very strongly was that it was a very high, I think the scale is 0 to 10, it's a high level of readiness. There's lots of experience there already. Pretty high temperatures, so there's a lot of applications you could use it. And really it's an evolution of the advanced gas-cooled reactor. It is an open fuel cycle, which is its downside, but it was felt that the UK's experience with Magnox and AGRs could reduce the cost. As far as I'm concerned, all the people who were involved in the design of those systems are like me. You know, we're not going to be there to give advice. But we do have operational experience, I guess, still there. Okay, we've had a quick look at Magnox reactors in the UK, gas-cooled, graphite moderated, not particularly powerful. The advanced gas-cooled reactors, 4 of which are still operating, with the heat exchangers within the pressure vessel rather than external, but otherwise much the same, but with enriched uranium and using carbon dioxide as a coolant. The pressurized water reactors, which, well, I'm hoping that I'm going to see them actually producing power, but we'll wait and see. And then small modular reactors, which everyone, not just in this country, but throughout the world, everyone is saying this is the way to go. This is the way to try and contain the effort for design, the cost of producing, and the flexibility of how many you deploy in different places. Remember, our national grid system was designed on the basis of having large power points at various points, all feeding power out into the grid. That is no longer the case. My understanding is that all of the sites that have been identified for the first SMRs are the existing nuclear sites. And that sort of makes sense because you've got the infrastructure, you've got the knowledge, you've got the access into the grid. But in theory then, they can be deployed in various places. So you can imagine people with large data centers wanting a small modular reactor nearby to provide them with their power. Yeah, one thing I did see, and I forgot to mention as we went through, I think with Hinkley Point B, the agreement is that we will buy power from them for something like £95 per megawatt hour. And Jim Radcliffe, the CEO of INEOS, said, no one will buy it for that. And he's negotiated a contract with France to sell him electricity for less than half of that. So we'll see what happens to our electricity bills once these PWRs start coming online. Anyway, small modular reactors believed to be the future pretty much around the world. But people are thinking of advanced modular reactors, what is coming on beyond those SMRs. And at that point, you will be pleased to know that I can stop talking for a while. Maybe that we have some experts in the audience who know more than I do about some of these things.
Questions? Mike?
Yes, okay. You mentioned thorium earlier on, which seems to have a number of advantages.
Yeah.
But not much effort's gone into developing it. Do you see any future for thorium reactors?
You'll notice that all of the thoughts, both on SMRs and the advanced reactors, advanced modular reactors, are all uranium cycle.
Yeah.
And I think there's been so much invested in the uranium cycle that it's going to take a country that doesn't worry about the cost. So China might look at the thorium cycle and say, we'll build something, not worrying about the finances involved. And so it might develop, but it's going to be some way off, I'd have thought. That's a personal view. I mean, I don't have anything to back it up.
Question?
The Rolls-Royce reactors, they said they could build in 4 years. Do you believe that, or do you think that's just sort of marketing? That seems incredibly quick.
It is. Now, a few years ago, we had a talk here from Advanced Manufacturing, AMRC, Advanced Nuclear Manufacturing or something. Anyway, it's in Sheffield. But it was set up to look at the manufacturing technologies for SMRs. At that time, they were planning to build the pressure vessel themselves. And in Sheffield, they were building I think it was a third scale model, testing out things like electron beam welding and various other techniques to build that. Now I understand that Rolls-Royce have decided not to build the pressure vessel themselves, but to outsource it. So someone like Sheffield Forge Masters or so, to get that bought in. Now that may be because they thought it was going to take them too long to fit that into their program of building, and that to be able to meet those sort of timescales, they'd have to outsource it and get other people to provide it. I don't know. It does seem ambitious, particularly for the first one. The cost, as far as I'm aware, the costs that they've associated with the reactors, with the UK SMR, are based on something like the 9th unit that they build. So they're expecting it to be quite top heavy at the beginning, but then gradually decrease as time goes on. Again, just personal views. Yeah. Mike?
Question, Mike?
Yes, I don't think you mentioned a fast breeder reactor. Where does that fit in? Fast reactors.
Well, remember I said uranium-238. There's about, within natural uranium, there's something like 0.7% is uranium-235. So not a lot, and that's why they enrich the uranium to get a higher percentage of the fissionable material. If you're using natural uranium, you have to start them off by putting some neutron source in there. You've got to give them some neutrons to get things going. Once they've been running for a while, then you're okay. Sorry, I've forgotten what